Close your eyes and imagine an endless sea of swaying sugarcane, stretching beyond the horizon under a blazing sun. Each stalk a promise of the world's sweetest commodity. Now, picture colossal factories humming with activity, where those simple green stalks transform into millions of tons of pure, sparkling sugar crystals every year. From the moment sugarcane is cut in the field to when refined crystals tumble into bags bound for markets worldwide, this is a story of raw nature harnessed by cutting-edge technology, precise chemistry, and relentless human effort. In this documentary-style deep dive, we'll walk through massive cane fields, step into steam-filled extraction halls, and watch as thick, amber juice becomes white gold. Strap in as we uncover how sugar, an ingredient that fuels economies, kitchens, and our very cravings, is produced in bulk at a scale few of us ever imagined. Sugar begins in the field with sugarcane, Saccharum officinarum, a tall tropical grass capable of growing up to 15 feet in optimal conditions. Farmers choose high-yield, disease-resistant varieties, such as Co 86032 in India, LC P85-384 in the United States, or RO C22 in Brazil, based on climate, soil type, and desired sucrose content. Selection matters. Each cane stalk's sugar concentration, Brix level, can range from 12% to 18%, and small improvements in variety can significantly boost yields for million-ton factories. Planting typically occurs at the start of the rainy season. Mechanized planters insert 2 to 3 foot cane cuttings into neatly spaced furrows, about 30 to 45 centimeters apart, ensuring adequate room for root and stalk development. These cuttings, called sets, sprout new shoots as they decompose. Over 12 to 18 months, each sprouted set grows into a thick, fibrous stalk divided into nodes, with dense leaves capturing sunlight for photosynthesis. Farmers rotate cane with legumes like soybeans or beans between cycles to replenish soil nitrogen, breaking pest cycles and improving long-term productivity. Routine field management involves precise irrigation scheduling, often via drip or furrow systems, applying just the right volume of water to maximize sucrose accumulation without promoting disease. Soil tests guide balanced fertilizer application, combining nitrogen, phosphorus, potassium, and micronutrients like magnesium and boron. Extension officers monitor for pests such as the sugarcane borer and diseases like red rot or smut. When early signs appear, targeted interventions, biological controls, pheromone traps, or minimal-use fungicides protect yields while minimizing environmental impact. Before harvest, agronomists conduct periodic Brix testing, sampling stalk juice with portable refractometers to ensure optimal sucrose levels. When average Brix readings hit 16 to 18% and soil moisture conditions are stable, harvesting begins. Harvesting vast sugarcane fields requires an army of workers and machines. In regions like Brazil, Thailand, and India, home to the world's top sugar producers, mechanical harvesters dominate. These towering machines bite cane stalks near ground level, strip leaves, and load trimmed stalks into adjacent trailers in one seamless operation. Mechanical harvesting slashes labor needs by up to 80%, reduces harvest time, and ensures rapid transport to the mill. However, excessive handling can bruise stalks, risking sugar loss through early microbial activity, so operators calibrate harvesters daily to account for field conditions and cane maturity. In smaller farms or regions where terrain is unsuitable for machines, such as steep slopes, laborers still harvest by hand. Using machetes, they carve stalks at the base, then stack them in bundles before loading onto tractors or animal-drawn carts. Though slower, hand harvesting minimizes stalk damage and increases juice yield per ton. Timing is crucial. Once cut, cane sugar begins converting to invert sugars, glucose and fructose, which are harder to crystallize. Therefore, mills strive to process harvested cane within 24 hours. Trucks or rail cars ferry fresh cane to the mill front gates, where each load is weighed on high-precision scales. Weighbridge operators record weight data to calculate factory throughput and track field performance. Cane then moves to initial inspection areas, where each load receives a quick visual survey to remove extraneous material, stones, trash, or large leaves before entering the mill. At the mill entrance, conveyor belts transport cane bundles to the washing station. High-pressure water jets strip away remaining soil, small pebbles, and loose leaf matter. Washed cane then feeds into massive cane cutters, knife rolls or shredder drums, that chop stalks into 4 to 6 inch pieces called billets. This increases surface area for subsequent extraction and speeds up processing. Modern mills often use dual roller shredders equipped with textured surfaces to maximize juice release while minimizing fiber damage. Next, the billets pass through a series of crusher mills or heavy-duty roller mills. Each mill consists of large grooved rollers, sometimes measuring 1.5 meters in diameter, powered by high-torque motors. As cane moves through successive mills, typically 3 to 5 stages, rollers crush the billets, extracting juice and separating fibrous material known as bagasse. Juice flows by gravity into clarified extraction tanks, while bagasse, the pulpy residue, emerges from the final mill at about 45 to 50% moisture content. Bagasse isn't waste, it fuels the mill's boilers. Mills use high-pressure boilers, often operating at 700 to 1,200 pounds per square inch, to burn bagasse in efficient, staggered grate furnaces, generating steam that powers turbines for electricity and provides process steam for heating. This cogeneration model supplies up to 80% of the mill's energy needs, drastically reducing reliance on fossil fuels and lowering production costs per ton of sugar. Cane juice, still containing 10 to 15% suspended solids, known as mud, proceeds to the juice clarification stage. Raw cane juice contains impurities, soil particles, waxes, proteins, and organic compounds that must be removed to yield pure sugar. In a step called clarification, juice combines with lime, calcium, hydroxide, and sometimes a small amount of phosphoric acid. This pH adjustment induces impurities to coagulate into flocks. The mixture moves to clarifier tanks, large, cylindrical vessels where clarified juice flows horizontally, allowing flocculated solids to settle by gravity. Many modern factories add flocculants, like polyacrylamide, in controlled doses to accelerate settling. Settled solids, called mud, collect at the bottom, periodically drawn off and recycled as fertilizer, improving soil pH and supplying organic matter back to cane fields. Clarified juice, now called thin juice, contains around 12 to 15% sucrose, free of large particulates. Thin juice then enters multiple effect evaporators, MEE. In these towering columns, steam from boilers heats the first effect, vaporizing water and concentrating juice. The vapor from one effect condenses to heat the next, cascading through 4 to 6 effects and conserving energy. By the final effect, concentrated juice, now thick juice, reaches 60 to 65% solids. Automated controls govern steam pressure, often 2 to 3 bar in the first effect, decreasing by 0.5 bar each subsequent stage, and juice flow rates to maintain uniform concentration and prevent caramelization. thick juice moves to vacuum pans, sealed kettles where it boils under reduced pressure, around 0.4 to 0.6 bar at temperatures near 105 to 110 degrees Celsius. Operators add seed crystals, fine sugar crystals collected from previous batches, to initiate sucrose crystallization. Agitators gently stir the supersaturated juice as it cools under vacuum, letting microscopic crystals form and grow uniformly. After 30 to 45 minutes, crystals reach target size, about 0.2 to 0.3 millimeters, and the mixture, referred to as massacute, is diverted to centrifuges. Centrifuges are high-speed, perforated drums, sometimes spinning at up to 3,000 RPM, lining the inner walls with a fine cloth filter. As massacute enters the centrifuge, centrifugal force separates sugar crystals from the liquid mother liquor called molasses. The sugar cake, still wet, approximately 2 to 3% moisture, emerges from the centrifuge with a cake discharge cycle. Robots or automation arms sometimes shake the centrifuge basket to release the cake, depositing it onto conveyor belts for further processing. Meanwhile, molasses flows out through perforations and is collected for distilleries, animal feed, or reprocessing in subsequent boiling cycles. Molasses with high non-sugar content, Family 3 molasses, is sold to ethanol producers for biofuel, while first-pressed juice yields cane syrup or blackstrap molasses used in baking, animal nutrition, and fermentation industries. This multi-product approach maximizes profitability and ensures minimal waste. Impurities, ash, colorants, and trace minerals. Most markets demand white refined sugar, so raw sugar undergoes affination and refining. Affination begins by mixing raw sugar with a syrup solution, about 15 to 25% solids, heating the mixture to dissolve the outer layer of crystals and wash away surface impurities. Molten sugar drains off, leaving clean seed crystals to re-enter centrifuges and detector machines. Next, the seed crystals travel to melters, heat exchangers where sugar dissolves in water to form a clear syrup. This syrup, 40 to 50% solids, feeds to defecation tanks, where heated syrup mixes with lime and carbon dioxide, carbonatation process. This chemical reaction precipitates calcium carbonate, trapping fine particles and color bodies. Filtered syrup moves to decolorization vessels containing activated carbon or ion exchange resins, absorbing remaining colorants. The resulting syrup, now nearly transparent and above 99.5% sucrose, enters vacuum pans for a second crystallization cycle, ideally yielding uniform, snow-white crystals known as refined sugar. Dried sugar crystals tumble into large rotary sifters, rotating cylinders with internal mesh screens separating any oversized lumps or fines. Oversized crystals, bumpy sugar, return to refining loops, while oversized fines become sand sugar used in specialty candy production. Once sieved, sugar flows to hoppers, feeding packaging machines. Bulk packaging lines weigh customer-specified quantities, 1 kilogram. 5 kilograms, 25 kilograms, or 50 kilograms into laminated paper bags or heavy-duty polypropylene sacks. Auger fillers ensure precise weight measurement, error margin within plus or minus 0.2%. Bagged sugar passes under metal detectors to catch stray machinery fragments, then goes through automated check weighers to confirm exact weight. Filled bags seal via high-speed sewing machines or heat-sealed film, depending on packaging type. For industrial customers, bakery chains, beverage bottlers, and dairy processors, sugar ships in 1-ton flexible intermediate bulk containers, FIBCs, lined with polyethylene to keep out moisture. Palletized loads shrink wrap and stack onto refrigerated or ambient trucks, depending on climatic conditions and transit duration. Retail packs move through distribution centers to supermarket shelves, where attractive branding highlights 100% pure cane sugar, non-GMO, or organic labels to capture consumer attention. Throughout production, quality labs operate around the clock. Samples from each batch undergo rigorous analysis. Moisture content measured by Carl Fisher, titration, or infrared moisture analyzers. Color measured in ICUMSA units, International Commission for Uniform Methods of Sugar Analysis. Ideally, below 45 ICUMSA for white refined sugar. Ash content determined by incinerating samples at 900 degrees Celsius in muffle furnaces, revealing non-sugar mineral residues, and polarization tests, using polarimeters, confirm sucrose purity above 99.7%. Impurity tests, such as conducting ash density, dextran content, and turbidity, ensure sugar meets specifications for food-grade or pharma-grade products. Microbiological analysis, plating on nutrient agar, verifies absence of coliforms, E. coli, salmonella, and other pathogens. Since sugar is a low-moisture environment, these tests guard against post-process contamination. If any batch fails, it's diverted to non-food applications, industrial ethanol, feed, or fermentation, rather than consumer markets.
Craft beer production in American factories. Millions of pints of craft beer being produced every year, each one bursting with unique flavors and aromas. How do American factories manage to brew such diverse and high-quality beers in bulk without losing their artisanal touch? Join us as we uncover the precise processes and cutting-edge techniques that transform raw ingredients into the liquid gold beloved by beer enthusiasts nationwide. From the first sip to the final packaging, discover the intricate journey that makes American craft beer a staple on tables everywhere. Selecting premium ingredients for craft beer. The foundation of any great craft beer lies in its ingredients. American craft breweries adhere to the German purity law of 1516, ensuring that their beer is made using only the finest components: water, barley, hops, and yeast. High-quality water is sourced from pristine locations, providing the perfect base for brewing. Specialty malts and a variety of hops are carefully selected to create diverse flavor profiles, while premium yeast strains are chosen to achieve the desired fermentation characteristics. Malting, preparing the barley for brewing. Malting is the first critical step in the beer making process. Barley grains are soaked in water to initiate germination, allowing enzymes to develop. This process converts the grain starches into fermentable sugars. Once the grains begin to sprout, they are carefully dried and roasted in kilns to produce malt. The roasting temperature and duration are meticulously controlled to develop specific flavors and colors in the malt, which will ultimately influence the beer's taste and appearance. Milling, grinding the malt for efficient extraction. After malting, the malt is stored in silos until it's ready to be milled. Milling involves grinding the malt into a coarse powder, which increases the surface area and facilitates the extraction of sugars during mashing. The malt mill crushes the grains without pulverizing them, ensuring that the husks remain intact. These husks play a vital role in the lautering process by forming a natural filter bed, which helps separate the liquid wort from the solid grain particles. Mashing, converting starches into sugars. The milled malt is then combined with warm water in a vessel known as the mash tun. This mixture, called the mash, is carefully heated and stirred to promote the activity of enzymes that convert starches into fermentable sugars. The temperature is gradually increased from around 45 degrees Celsius to 78 degrees Celsius, passing through various temperature rests that optimize enzymatic activity. This process, known as saccharification, is essential for producing a wort rich in sugars that yeast will later ferment into alcohol and carbon dioxide. Lautering, separating wort from grain. Once mashing is complete, the next step is lautering, where the liquid wort is separated from the solid grain particles. This is achieved in the lauter tun, where the mash is gently drained through a bed of grain husks, acting as a natural filter. Rotating blades or knives may be used to cut through the grain bed, ensuring a smooth flow of wort while effectively separating it from the spent grains. The clear wort is then collected for the boiling stage, while the spent grains are often repurposed as high-quality animal feed. Boiling, infusing hops for flavor and stability. The collected wort is transferred to a brew kettle, where it is boiled for up to 2 hours. During boiling, hops are added at various stages to impart bitterness, flavor, and aroma to the beer. The timing and type of hops used play a crucial role in defining the beer's character. Boiling also sterilizes the wort, eliminating any unwanted microorganisms and ensuring the beer's stability and shelf life. Additionally, proteins coagulate and precipitate during the boil, contributing to the beer's clarity. Whirlpooling. Clarifying the wort. After boiling, the wort undergoes a whirlpool process to further clarify it. The wort is rapidly circulated in a whirlpool tank, creating a vortex that draws the remaining hop particles and proteins into a central cone. This sediment, known as trub, is then separated from the clear wort. The whirlpooling step ensures that the wort is as clear as possible before cooling, which is essential for producing a high-quality final product. Cooling, preparing the wort for fermentation. The clarified wort needs to be cooled quickly to a temperature suitable for yeast fermentation. This is achieved using a plate heat exchanger, where the hot wort is passed through plates cooled by chilled water or glycol. Rapid cooling is essential to prevent contamination and to prepare the wort for the addition of yeast. The efficient heat exchange process not only cools the wort, but also allows for the reuse of extracted heat in other parts of the brewery, enhancing energy efficiency. Fermentation, transforming wort into beer. Once cooled, the wort is transferred to fermentation tanks where yeast is added. The type of yeast used, top fermenting ale yeast or bottom fermenting lager yeast, determines the style of beer being produced. In ale fermentation, yeast floats to the top, producing fruity and complex flavors at warmer temperatures. In contrast, lager fermentation occurs at cooler temperatures, resulting in a cleaner and crisper taste. During fermentation, yeast consumes the sugars in the wort, producing alcohol and carbon dioxide, which give beer its characteristic effervescence. Conditioning, maturing the beer. After primary fermentation, the beer enters the conditioning phase. This stage involves storing the beer in temperature-controlled tanks for several weeks to months, allowing flavors to mature and unwanted byproducts to settle. Conditioning helps in developing the beer's final taste profile and clarity. During this time, additional hops may be added for dry hopping, enhancing the beer's aroma without increasing bitterness. The extended maturation ensures a smooth and well-balanced final product. Filtration, achieving clarity and stability. Once conditioning is complete, the beer undergoes filtration to remove any remaining yeast, proteins, and particulates. Filtration can be achieved through various methods, including plate and frame filters or membrane filters. For certain beer styles, such as hoppy IPAs, a lighter filtration process is preferred to retain more flavor and aroma compounds. Proper filtration not only enhances the beer's clarity, but also improves its shelf stability by removing elements that could cause haze or spoilage. Carbonation, enhancing flavor and mouthfeel. Carbonation is a critical aspect of beer production that affects both flavor and mouthfeel. After filtration, carbon dioxide may be injected into the beer to achieve the desired level of effervescence. Alternatively, natural carbonation can occur during fermentation if the beer is bottled or kegged with a small amount of residual sugar and yeast. The right level of carbonation enhances the beer's aroma, balances its flavors, and provides a refreshing sensation when consumed. Packaging, bottling, canning, and kegging. The final stage in bulk craft beer production is packaging. Beer is filled into various containers, including bottles, cans, and kegs, depending on distribution needs and consumer preferences. Automated packaging lines ensure that the beer is filled under hygienic conditions, minimizing exposure to oxygen and contaminants that could degrade quality. Advanced sealing techniques preserve the beer's freshness, flavor, and carbonation, ensuring that it reaches consumers in optimal condition. Quality control, ensuring consistency and excellence. Throughout the brewing process, rigorous quality control measures are implemented to maintain consistency and excellence in every batch. Samples are taken at multiple stages, after mashing, boiling, fermentation, and packaging, and analyzed for factors such as alcohol content, bitterness, IBU, color, SRM, and clarity. Sensory evaluations, including taste tests, are conducted by expert panels to ensure that each batch meets the brewery's high standards. This commitment to quality ensures that consumers enjoy a reliable and exceptional product every time. Sustainability practices in craft beer production. Modern American craft breweries are increasingly adopting sustainable practices to minimize their environmental footprint. Energy-efficient brewing equipment, water recycling systems, and waste reduction initiatives are commonly implemented. Spent grains, a byproduct of brewing, are repurposed as animal feed or used in baking and other food products. Sustainable sourcing of ingredients, such as locally grown hops and organic barley, further supports eco-friendly brewing practices. These efforts not only benefit the environment, but also resonate with environmentally conscious consumers. Technology and innovation in bulk. Brewing technology plays a pivotal role in modern bulk craft beer production. Advanced automation systems streamline various stages of brewing, from ingredient handling to packaging, enhancing efficiency and consistency. Data analytics and real-time monitoring enable breweries to optimize processes, reduce waste, and maintain precise control over every aspect of production. Innovations such as automated fermentation controls, smart sensors, and AI-driven quality assessments are revolutionizing the craft beer industry, allowing breweries to produce high-quality beer at scale. Scaling craft beer production without compromising quality. Scaling up craft beer production to meet increasing demand while maintaining quality is a significant challenge for American breweries. To address this, breweries invest in scalable brewing systems that allow for flexible batch sizes and consistent results. Process optimization, meticulous ingredient sourcing, and robust quality control protocols ensure that large-scale production does not compromise the unique flavors and characteristics that define craft beer. By balancing tradition with innovation, American breweries successfully deliver artisanal quality beer to a broader audience. Distribution and logistics of bulk craft. Beer-efficient distribution and logistics are essential for delivering bulk craft beer to markets nationwide. Breweries collaborate with distributors to manage inventory, transportation, and storage, ensuring that beer remains fresh from the brewery to the consumer. Cold chain logistics are often employed to maintain optimal temperatures during transit, preserving the beer's quality and preventing spoilage. Strategic distribution networks and partnerships enable American craft breweries to reach a wide range of retail outlets, bars, and restaurants, expanding their market presence. The future of bulk craft beer production in America. The future of bulk craft beer production in America is bright, with continued growth and innovation on the horizon. Emerging trends include the development of new beer styles, experimentation with unconventional ingredients, and the integration of cutting-edge technologies to enhance brewing efficiency and sustainability. As consumer preferences evolve, breweries are increasingly focusing on personalized and localized beer offerings, catering to diverse tastes and supporting community engagement. The commitment to quality, creativity, and sustainability ensures that American craft beer remains a dynamic and beloved industry for years to come. The art and science of bulk craft beer. Brewing bulk craft beer production in American factories is a harmonious blend of art and science, where traditional brewing methods meet modern technology to create exceptional beverages. From selecting premium ingredients to implementing sustainable practices, every step in the process is meticulously managed to ensure the highest quality beer. As we've explored, the journey from grain to glass involves a series of carefully controlled stages, each contributing to the unique flavors and characteristics that define American craft beer. Whether enjoyed at a local brewery or purchased from a store shelf, each pint represents the dedication and passion of countless individuals committed to the craft of brewing. Thank you for joining us on this exploration of bulk craft beer production in factories. If you enjoyed this video, be sure to like, subscribe, and hit the notification bell to stay updated with our latest content. Cheers to great beer this new year and the incredible craftsmanship behind every bottle. Welcome to our channel, where we dive deep into the fascinating world of slime manufacturing. In this video, we will explore how slimes are made in bulk in factories, offering you a behind-the-scenes look at the process. As a slime enthusiast or potential entrepreneur looking to understand bulk slime production, you will learn about the intricacies of the slime factory, the materials used, and the methods employed to create a variety of slimes at scale. Understanding the slime factory environment. Slime factories are fascinating spaces where creativity meets science. The production environment is often filled with vibrant colors, mixing tanks, conveyor belts, and quality control stations. In this section, we will walk you through the factory floor, highlighting how each step is optimized for efficient mass production. Whether you are curious about how slime is mixed, colored, and packaged, or interested in the machinery behind bulk slime production, this comprehensive tour covers it all. We will also discuss safety protocols and hygiene standards that ensure the highest quality product. The ingredients behind the magic bulk slime production begins with sourcing high-quality ingredients. Factories purchase materials such as glue, water, borax, activators, pigments, glitters, and foam beads in large quantities. Each ingredient plays a key role in crafting the perfect slime texture, elasticity, and color. By analyzing the chemical reactions and ratios involved in slime making, viewers gain insights into why certain combinations yield different textures, from fluffy and airy to thick and stretchy. The mixing process, from raw materials to slime. Once the ingredients are ready, the actual manufacturing process starts with mixing. Bulk slime is produced using large industrial mixers that combine glue, water, and additives on a massive scale. Automated mixing systems ensure consistency and quality throughout production. The process is carefully monitored, adjusting the ratios to achieve desired textures and colors. Voiceover narration will take you through the step-by-step procedure, emphasizing terms like bulk mixing, automated slime production, and industrial slime process. Automation and technological advances. The role of automation in slime factories cannot be overstated. Modern factories use computerized systems to regulate temperature, viscosity, and mixing speeds, ensuring each batch of slime meets strict quality standards. Technology like programmable logic controllers, PLCs, and robotic arms streamline operations, reduce human error, and increase output. By including phrases like automated slime factories and technology in slime production, this narration not only guides viewers through the factory tour, quality control and consistency. Maintaining consistency in bulk slime production is crucial for customer satisfaction. Quality control measures are implemented at every stage of the process, from raw material inspection to final packaging. In the quality control rooms, experts test viscosity, stretchability, and color uniformity to ensure each batch meets predetermined standards. This attention to detail prevents defects and ensures that consumers receive high-quality slime every time. Safety and environmental considerations. Factories prioritize safety and environmental considerations when manufacturing slime. Proper handling of chemicals, waste management, and safety protocols protect both workers and the environment. In this section, we discuss the eco-friendly practices adopted by slime factories, including recycling materials, minimizing waste, and adhering to local safety regulations. Using keywords such as eco-friendly slime manufacturing and safe slime production not only positions the content well for search engines, but also shows viewers the ethical side of bulk slime creation. Varieties of slime produced in bulk. Slime factories produce a wide variety of slime types to cater to diverse customer preferences. From classic stretchy slimes to glittery, fluffy, and crunchy variants, each type requires a unique recipe and production technique. The factory floor buzzes with different mixing stations dedicated to each variety. As we describe the process for making different slimes, custom colors and effects. Customization is a significant aspect of the slime industry. Factories often produce slime in a spectrum of colors, adding effects like glitters, beads, and scents to create unique products. This part of the narration explores how colorants and additives are mixed into batches and how adjustments to the process can yield slimes with mesmerizing effects like glow-in-the-dark or aroma-infused varieties. Packaging and bulk distribution. Once the slime is produced, the next step is packaging. In bulk slime factories, automated packaging lines fill containers or bags with slime, seal them, and label them for shipment. This efficient system ensures that packaging is consistent and safe for transport. We'll explain how different packaging designs cater to various markets, whether for retail displays, online orders, or special promotional boxes. The business of slime, market demand, and trends understanding. The market demand for slime helps factories adjust production volumes and innovate new products. The popularity of slime on social media platforms, coupled with its educational and stress relief benefits, has driven an explosion in demand. This part covers how consumer trends influence factory production decisions, from increasing certain textures to exploring new ingredients. The science behind slime creation. Behind every perfect batch of slime lies a fascinating blend of chemistry and physics. This section will delve into the science behind slime creation, the polymer chains that give slime its elasticity, the cross-linking agents that transform liquid into goo, and the effects of additives on texture and appearance. By demystifying the science, we not only educate our audience, but also optimize for keywords like slime chemistry, polymer science in slime, and how slime works. This detailed explanation caters to viewers interested in learning more than just the surface details of slime production. Sustainability in slime manufacturing. Sustainability is increasingly important in every industry, including slime manufacturing. Factories are now implementing eco-friendly practices such as using biodegradable materials, reducing waste, and optimizing energy consumption during production. By spotlighting these initiatives, the narration appeals to environmentally conscious viewers. Incorporating keywords like sustainable slime production, eco-friendly slime factory, and green manufacturing practices not only highlights positive industry changes, customization for bulk buyers. Bulk slime manufacturing offers customization for retailers, schools, and entertainment venues. Factories work closely with clients to produce slimes tailored to specific themes, events, or branding requirements. This could mean creating slimes in corporate colors, scented slimes for sensory play, or themed slimes for parties. We will discuss how businesses approach slime factories for custom orders, negotiate quantities, and influence production processes. Quality assurance and customer satisfaction. In bulk production, quality assurance is key to maintaining customer satisfaction. Factories often implement multiple checkpoints where samples are taken and tested for compliance with safety and quality standards. Customer feedback loops are established to continuously improve the products based on reviews and market response. By emphasizing customer satisfaction and quality assurance in slime manufacturing. Marketing slime in the digital age. The rise of social media and digital marketing has revolutionized how slime products are promoted and sold. Factories collaborate with influencers, run online campaigns, and leverage platforms like YouTube, Instagram, and TikTok to reach slime enthusiasts. The impact of bulk slime production on the economy. Bulk slime manufacturing isn't just about creating fun products, it also contributes to the economy. Factories create jobs, support local suppliers, and drive exports. By discussing economic benefits, investment opportunities, and market growth, we provide a comprehensive look at how the slime industry fits into larger economic trends. Tips for aspiring slime entrepreneurs. For viewers dreaming of entering the slime business, this section provides valuable tips on starting small, scaling production, and understanding market dynamics. We cover essential considerations like sourcing quality ingredients, complying with safety standards, and marketing products effectively. The future of slime, trends and innovations. Looking ahead, the slime industry shows no signs of slowing down. New trends such as biodegradable slime, educational kits, and sensory-friendly products are emerging. Factories are investing in research and development to innovate and stay ahead of consumer demand. We will explore potential future advancements in slime production, like smart slimes that change color with temperature or incorporate interactive elements. The journey of how slimes are made in bulk in factories is a blend of art, science, and business acumen. From the initial mixing of ingredients to final packaging and shipping, every step is crucial in delivering quality products to consumers worldwide. We hope this detailed narration has provided you with insights into the fascinating world of slime manufacturing, answered your questions, and sparked new interests. Remember to subscribe to our channel for more in-depth tours, industry insights, and creative tutorials related to slime and other DIY crafts. Thank you for watching, and we look forward to exploring more exciting topics with you.